Welcome back. In this video, we're going to define the definite integral. But before we do that, I just want to quickly recap what we've previously talked about. We're looking at the area under these curves on a certain interval from A to B, we're calling it. We're going to use n rectangles to approximate the area. But then we've recently just discussed that we're now going to look at n going to infinity. Importantly, on every interval, this xi star represents any point on that interval. It doesn't have to be the initial or the end point or the midpoint. It can be any point on that interval. And delta x, which represents the width of those intervals, is defined as b minus a over n, or the length of the interval divided by the number of subintervals you want to break it up into. Then with that setup, what we do is we compute the areas of each of those rectangles in those intervals. So the first rectangle would be this right here, x sub 1 star times the width, which is delta x, plus the second interval's rectangle would be x2 star times delta x. And we do that all the way to the last interval, which is the xn interval. We got that function value times the delta x. And this then we've defined as the Riemann sum, which we can write in sigma notation in this way, from I equals 1 to n of these x sub I stars times delta x. And finally, we've said if we let n go to infinity, this now defines the area under that curve given a continuous non-negative function. So then here is our definition of the definite integral. The setup is exactly as we described. So we have a function that's defined on this interval AB. Our delta x is the size of these subintervals, which is found by b minus a over n equal size subintervals. And as xi star is going to represent any point on the ith interval. Then the definite integral of f on AB is defined as this. The notation we use is this right here, from a to b of f of x times dx. And this equals exactly what you would expect. It's what we found previously. This equals the limit as n goes to infinity of the summation from 1 to n of x, or f of xi star times delta x. And lastly, just a vocab thing, if this limit exists, we say that f is integrable on AB. All right, it took quite a bit of setup, but now we have it, the definite integral. This is our main player here this quarter. We want to look a little bit more at this notation and talk just a little bit about it. So this notation right here is representing what is being described by this limit and the Riemann sum. So specifically, this part right here is the condensation, if that's a word to say here, of these symbols right here. So this means the limit of a summation. And that's a really important point to remember throughout this class. We're going to go in and out of actually thinking about these as summations because we're going to have a bunch of properties that let us circumvent some of the dirty work that we have to do. But it's really important to understand that this, for a derivative, it was always just the limit of this difference quotient, right, of finding the slope. But there's two things in play right here. This symbol of the integration means that the limit applied to a summation, really important. And then also you'll notice an interesting thing about this notation. This delta x right here turns into this dx that you'll remember from differentiation. The idea is that this is the same as this. So all dx represents is a change in x, right, of these differentials. And hopefully you remember seeing that towards the end probably of your differential calculus class. The dx represents the fact that this change in x is infinitesimally small. So importantly, a statement of this is that as n goes to infinity, or as the number of subintervals, the number of these rectangles you create on this interval goes to infinity, the change in x goes to 0, or more specifically, the change in x becomes infinitesimally small. We represent that as this dx. And last thing I want to point out with the notation that you'll most likely forget as we have all this new stuff we're going to learn is the fact that this represents a multiplication of these function values times these small changes or the width of these intervals. Now that we've introduced the definite integral, we need to get a couple theorems under our belts and a little bit more understanding about what this integral is actually computing in order to actually work with it. First up, if we have a function f that is continuous on AB, or as I alluded to in a previous video, if f has a finite number of discontinuities, by the way, that was this trick right here, finite number of discontinuities, was the reason for this xi star, so we can kind of jump around discontinuities. But if this is true, so if it's either completely continuous on AB or only has a finite number of discontinuities, then we know for a fact that f is integrable on AB, meaning the definite integral on A over AB exists. Next thing to say, and this is really important, is that we've built this with the idea that we're finding the area under the curve, which when your function is non-negative is exactly what the definite integral will be computing. But as you'll see in the definition we have for the definite integral, we're now not limiting this to non-negative function values. So in this function, we go below the curve. Importantly, with the way this is defined, and because down here, these function values that we'll get out are negatives, in this case, when we compute the integral on when our function is above the x-axis, or when we have positive function values, these will output positive integral values. So the integral will be positive here until this is 0. And then here, between these roots of this function, the integral will actually output negative values. And then here, after this root right here, this function would again output positive integral values. This fact will have a lot of different consequences throughout this quarter, but it's really important. I want to emphasize this. If I wanted to calculate the area between the curve and the x-axis from A to B in this case, I couldn't just evaluate the definite integral from A to B. Because what would happen in that case is these positive areas would be canceled out in some sorts by this negative area. If I want to find all of these areas together between the function and the x-axis, what I would need to do is to compute the definite integral between A and this first root, and then calculate the area here between these two roots and the area between here, knowing that I'm going to get a negative out. But if I got a negative value for the definite integral here, I'd want to translate that into a positive value if I'm thinking about solely area. That said, there's nothing wrong, and you'll see the applications of having negative integral values, but it's just important to understand the consequence of dipping below and above the x-axis, and you'll see more of that very soon. All right, one last theorem before we can actually start doing the work of computing or evaluating these definite integrals. In this case, all we need is f to be integrable on AB. We just found out that f is integrable on AB if it's continuous on AB or has a finite number of discontinuities. In this case, what we're going to be allowed to do is instead of just having this random point on the ith interval or this I star, we can designate a specific point, which will give us a formula for easily computing these definite integrals. More specifically, what we're going to say, so if we're looking to compute this definite integral and we know it exists, then we can always compute it by using simply the right endpoints, which will make our lives a lot easier. And so this will look very, very similar to the definition. The big difference is how we're defining the function values here. So this will be f of xi. These are the right endpoints. And just to clarify this real fast, delta x is what we've always known it to be. It always is b minus a, the length of the interval divided by the number of subintervals. And this x sub I is going to be a plus I times delta x. Again, that should make a lot of sense. All that is saying is if A is the first part of the subinterval, the next subinterval starts, or the end of the first one, is at this point right here where you add this delta or the length of the interval. So you start with this point and you're going to add this to find all of the next endpoints for all of the intervals. And importantly, I sub 1, or the first one, isn't a, it's a plus that delta x. So just to recap before we move to the first example, if we can show that f is integrable, this means if we can show easily if it's continuous on this interval, then we have delta x to be defined in this way, and we have our xi's defined like this, then we can compute this definite integral by computing this sum limit. So then our first example is, in my mind, as it should be. We're computing the definite integral from 0 to 2 for x squared. And previously, we did approximations of this and have a bounded range for what this value is for the area under x squared from 0 to 2. But now we're going to give a rigorous proof of the exact value of that area. As we set this up, first and foremost, we need to remember that our delta x's, in these cases, are found by b minus a over n. And then our xi term is defined as a plus I times this delta x. So in this context for this definite integral, our delta x would be 2 minus 0 over n, which would be 2 over n. So that's our delta x in this case. Our xi is a plus I times that delta x. So a is 0 in this case. It's the starting point for this interval. And then plus I times delta x, which is 2 over n, which this obviously doesn't do anything to 0 here, so we'll write this as 2 over n times I. Now what we're going to do is we're going to rewrite this with the limit sum definition we just had. So in this case right here, this is the limit as n goes to infinity of the summation from 1 to n of f of xi. Xi in this case is represented by this 2 over ni times delta x, which is 2 over n. The next thing, f of 2 over ni, well, I know my function f in this case is x squared, so I'll plug this into x squared, which means I'm just going to square this expression right here. Then I'm going to clean this up a little bit. I'm going to apply this exponent of 2 to all of these factors here. Okay, now we have a really important move. In this case, remember, n, in terms of this sum, is a fixed number. It doesn't vary in this case. It varies for the limit. We got to be careful. But in this case, n is a fixed number of this sum, meaning this right here and this right here, these factors are all constants. They don't change as this summation iterates up from 1 to n. So what we can do, using that constant multiple property that we discussed in a previous video, we can pull out these factors and put it out in front of the summation. And importantly, we can't put them outside the limit because n varies for the limit, but it doesn't vary for the sum. That's a really important trick, and you'll do that constantly with these definite integrals. So what I'll have in this stage is the limit as n goes to infinity of, I'll pull these both out, what I get is 8 over n cubed times the summation from 1 to n of I squared. Okay, we've done actually most of the big work with this summation. We're going to be dealing with the limit here in 1 second, but I just want to recap those steps because it can feel pretty foreign in the beginning. So I have generally this definition here, but I'm going to be using the right endpoint strategy for finding these xi's. How I do that is first by finding this delta x, which is just the length of the interval divided by n. Again, n we're going to leave as this variable, but it's a constant in this case. So we get 2 over n. And then we can define the xi, so every term that we're going to actually find the function value for the height of these rectangles. In this case, that's a plus I times xi, which gives us in this case 2 over n times I. Then what we do are plug that delta x in here and the xi inside the function. We'll have the function, if we're asked to find this definite integral, we'll have the function. So plug this 2 over ni in this case into the function x squared, which gives us this. Then at this point, the only things that will vary are things that have these factors of I in them, because I changes for every term of this series. I'm pulling out this 4 over n squared and the 2 over n because they're constants outside of here. This makes it easier for me to compute this summation. And now you'll see from the previous experiences, this is actually a summation that we can define. We have a property for this. In this case, to remind you, is that the summation from 1 to n of I squared equals n times n plus 1 times 2n plus 1 all over 6. And so what we're going to do now is we're going to input that in for this summation statement. And what that will do, you'll see, and I'll do that in 1 second, is that then we no longer have a summation to deal with. We use this to deal with it. Now we just need to figure out this limit as n goes to infinity. And now what I'm going to do, since we have this infinite limit, we're going to be looking at like asymptotes, or thinking what happens to these terms as n goes to infinity. What I'm going to do now is expand this top right here, and then I'm going to move stuff around a little bit, and you'll see what I'm doing here. So all I did from here to here was I expanded this n times n plus 1 times 2n plus 1 to get this polynomial on top. Then what I did, because I want to interact these n's, right? I'm trying to get rid of these canceling some powers or deal with this polynomial here. So I moved this n cubed underneath, and this constant of 6 I put out here. And the reason for that is I'm going to interact this n cubed now with these. And as you know with limits, so now what I'm going to do is I'm just going to divide each of these terms. So what I'll get here is the limit as n goes to infinity of 8/6 equals, so this divided by that is 2 plus 3 over n plus 1 over n squared. Now, as n goes to infinity, I can calculate this. This is a constant, that's a constant. This term, as n goes to infinity, this goes to 0, and so does this. Meaning, as I apply the limit, what this becomes is 8/6 times 2, which is equal to 8/3, or in decimal form is 2.6667. I get a little awkwardly excited sometimes about first experiences where students see some of these things. And if you do have a feeling of being a bit overwhelmed, it's okay, that's natural. This is not as intense as it may seem. The notation kind of will throw you for a loop. These x sub i's, delta x's, and stuff like that. But these are all things you've previously seen. We're using this definition, and as I said, plugging in these. Our first work is to deal with the summation. So that summation, what we're trying to do is evaluate that and get an expression out of that. Generally, how we're going to do that is plug in that xi into the function. When we get here, pull out anything that's constant in terms of this summation right here, which we've done. The hope is that the only summations you have left are known summations that you can evaluate with our properties we previously discussed, which I did in this case, turn that into that. Then what you'll see is this is simply a limit, which you've dealt with way more than necessary previously. And our work then, however you deal with this limit is however you want. One thing I could have done, instead of doing this move from here to here, I could have simply said, well, this is a rational function. This is a constant. I could have moved the constant outside of the limit. And then say, well, since this is a rational function and we're looking at a horizontal asymptote, we look at the ratio of these lead terms right here, so that would be a 2. It's exactly the same argument. I just chose to do it this way right here. But long story short, we've now shown that the exact value under the function f of x equals x squared from 0 to 2 is 2.666 repeating, or 8/3, which is awesome. And again, no approximations. No gray area. We have an exact value of 8/3 for this area. In this second example, it's going to be a little bit more complicated just because of how things work out, but the process is exactly the same. What we're first going to do is calculate the delta x and the xi expressions. Delta x is b minus a. In this case, this will be from 4 minus 1 over n to give us a delta x of 3 over n. And then our xi is a. In this case, a is not 0, it's 1. That will make this a little bit more complicated. But plus I times 3 over n, excuse me, which I'll write as 1 plus 3 over ni. Now we can set up our limit sum here for this definite integral. So we have the limit again as x goes to infinity of the summation from n, starting at 1, going to n, of f of xi. I'm going to plug this in right now. So this is my function f of x. This is what I'm plugging in. So this will be 1 plus 3 over ni squared plus 2 times 1 plus 3 over n minus 5 times dx, or the delta x in this case, which is 3 over n. Okay, so all I've done right there is expanded this out, right? So I just foiled this out to get to this expression right here, distributed the 2 through there. Now that I have this, what I'm going to do is clean up this polynomial in terms of I. Again, just to repeat it, it's worth repeating, is that in this case, and I'm thinking about this inside this summation, n is a constant, I is my variable, my iterative variable, or my index. And so now I'm going to group these terms. I have one I squared term, 2 I terms, and I have my constants to put together. Now that I've cleaned everything up, I have some choices to make here. One thing that I could do, just to make it clear, I could factor out this 3n and put it out front. But because what I'm going to end up doing here in a second is splitting up this summation over these additions and subtractions using our properties that we've had previously, what I'll do instead is I'm just going to distribute this through. Again, this is just a choice that I'm going to make. I just don't want a bunch of nested parentheses. So I'm going to multiply that through, and I'll be finished messing with this inside the summation. Okay, now that I've distributed this 3n through, I've really done most of the dirty work of cleaning this all up. Now what I'm going to do, and I'm going to do this in 2 steps, just to not write so much out, but what I'm going to do is split this summation into over each of these terms right here, which I'm allowed to do, right? It's that property of the summation of AI plus BI is the summation of AI plus the summation of BI. So I can split this sum over these terms right here and attack each of them separately. But what I'm also going to do is the same move that I've been talking about and I did in the previous example. I'm going to factor out these constants out front here and put them out front of the summation. So again, now here's what I have. I've actually completely simplified these summations. This right here comes from this first term. I pulled out the 27 over n cubed outside here because it's considered a constant in terms of this. This n can't vary for this summation. It's a fixed value. I'm going to deal with this I squared exactly in the same way I previously did with that expression that we know equals this sum right here. And now I have this summation here. I'm going to apply a property that we know for these first n whole numbers from 1 to n. When you add those up, we have another formula for that. And this was I think the second property that we have. This is a constant, right? There's no I here, so each term is just 6 over n. So this is going to end up being 6 over n times n. What I'm going to do right now is I'll expand all 3 of these up over here. And again, while the algebra will start to look a bit messy as I expand this, all we're trying to do is to evaluate this limit now. At that point, we're just going to have these n expressions that don't have summations. We've broken them down, attacked each summation or each term separately, and our final work will just be to see if we can evaluate this limit. So here I've evaluated each of those sums, and again, all I've done was I've calculated the sum of from I equals 1 to n of I squared, which is this. Then I have the sum from 1 to n of I, which is that expression. Finally here, 6 over n again is just a constant in terms of this summation. So what I get is I get n terms of 6 over n, or n times 6 over n for this last term right here. Now, all I'm doing is dealing with the limit. What I'm going to do in this case is I'm now going to expand these just to help me see these lead coefficients that I need to analyze. And also I'm going to do the same move I just did a second ago. I'm going to move this constant of 6 over here and move the n cubed over here, and the same with this term also. Okay, I've really done all of the work then. What I've done there again is just expanded those numerators, moved these n factors underneath and the constants here. Now all I have to do is evaluate this limit. And I'm going to do this a bit more quickly than I did in the previous one, and this is how I suggest that you do it moving forward. we know that when you apply the limit to multiple terms, you can apply it to each term separately when calculating that. Also, when I apply the limit to this term, for example, the constant of 27/6 can move outside of the limit. And so I'm actually just evaluating the limit of this expression right here. which is a rational expression. I'll do that for this term also. This last term is just a constant of 6. The limit of any constant is just the constant itself. And so when I apply the limit to this term, I ignore the 27/6 for a second. This limit is, the limit as n goes to infinity is this horizontal asymptote that's 2 over 1, these lead coefficients. So this factor goes to 2. In this case right here, that should be an n squared in this case, excuse me. When I do this, these lead coefficients are 1, and so this goes to 1, and again, this stays at 6, giving me the value of this limit is 27/6 times 2 plus 36 over 2 times 1 minus 6. And then just to clean some of this up and show this all quick, I can cancel that with a factor of 2 there to get a 3. So this becomes 27 divided by 3 that we know is 9. This is 36 divided by 2, which is 18, and then minus 6. So if we have 9 plus 18 minus 6, this becomes 21. All right, let's finish this by just recapping what we did here. And again, this is exactly the same as the first example. There's just more going on. We had to expand this binomial because our x sub I was a little bit more complicated and whatnot. But just to walk through here, we first find our delta x, which is simple. It's just b minus a over n. That gave us this 3 over n. Then we plugged that with our a value of 1 into this expression right here to get our representative x sub I. Then we plug that into our function here along with our delta x. The steps will always be, we're going to deal with the summation. And in that case, we're just expanding. This is just pretty basic algebra, to be honest. Though, by the way, I hope this looked really smooth. This took me about an hour because I screwed up about 10 times as I did this, just to say that's going to happen to you too. That's okay. But fight and practice. Understanding the nitty gritty of this is really, really important moving forward. But I digress. Moving on, all I'm doing is simplifying this expression to here. That's straight algebra after I've done those plug and play first steps. Now what I'm doing is I'm using the properties of these sigmas, and the main properties are if you have multiple terms, split the sums over those terms to make your lives a lot easier. So I did that here. I've also pulled out these constants, and again, anything with an n in it in terms of this is a constant. The terms that have i's in them are not constant, or the factors that have I stay inside there. After you do that, then you're going to attack these summations with the properties that we have, which gave me these expressions right here. After that, it's nothing new with the sigma sum notations. All I'm doing is cleaning things up as much as possible so that I can evaluate the limits. And remember, if you have multiple terms for your limit statement, you can attack each of those separately. The limit as n goes to infinity of this first term, the next term, and the last term. And the last trick, just to remind you, and you'll get stuck if you don't remember this at times, I swapped out this n to the third with the 6, and you can do that. These are just denominators. I swapped those around because I want to analyze all of these n's together to make my life easier when evaluating that limit, which we found the definite integral of x squared plus 2x minus 5 from x equals 1 to x equals 4 is 21.